Hello. So this is the type of question that researchers often begin with when approaching endangered species. Before extracting any DNA or beginning to make conservation plans, they often look at statistics readily available to them, first to see how urgently conservation is actually needed. So in this question, we're looking at a rare population of monkeys living in the Sumatran rainforest that is being deforested. They are facing an extreme bottleneck, going from about 90 individuals to 8. They're left with 6 males and 2 females. And to see how much genetic variation they are losing, they're looking at the potential loss of heterozygosity over time. Heterozygosity equations are applicable to create nearly any prediction or move forward with creating management plans, as they are a common tool used to determine the loss of genetic material. So if heterozygosity is declining, organisms become far more susceptible to disease or their fatal events, as they cannot recover as quickly. And finding this initial data is important because otherwise researchers have little evidence to gain funding or base their claims off of. So the question is a good step-by-step look at how scientists may approach population with little information known, and they've just gone through a recent bottleneck. So by observing the loss of heterozygosity over time, gives a measure of how much is lost and where they can go from there. So first we're going to look at what is the effective population size. Effective population size is different from the actual population left. These are the individuals that actually have a chance of passing on their genes, given the amount of males to females. So the equation for this is going to be effective population equals 4 times the number of males multiplied by the number of females divided by the sum of the males plus females. So here we're looking at these numbers that were given. So we are going to have 6 males and 2 females, so you can just fill those in there. And this is going to give us equals 4 divided by 8. So the effective population size is only 6. So even though we have 8 individuals left, we can't assume that they're all going to mate since there is an uneven proportion of them. So next we're going to look at what is the proportion of heterozygosity following this bottleneck. So the equation for heterozygosity is H equals 1 minus 1 divided by 2 times the population during the bottleneck. So here we're going to be using our effective population size. So this will be 2 divided by 6. Make sure that you're not using the number 8. And this will give us 0.9167. So this is our proportion of heterozygosity immediately following the deforestation. From here, we can look at alleles. So originally the monkeys had 2 alleles. A was dominant for disease resistance, and little a was dominant or recessive for disease susceptibility. So the frequency of little a was 0.2, and we are looking for the allelic diversity trend following bottleneck. So if we know that little a was 0.2, we can assume that big A is 0.8, and we are finding this from P plus Q equals 1. So the equation for this, we're looking for the number of alleles following bottleneck. So we're going to use our original allele number, which is found up here. And this is minus the sum of 1 minus the allelic frequency times 2 times the population number. So here we have 2 minus 1 minus 8 plus 1 minus 0.2, like this. And this is going to give us 1.931. So now, allelic diversity is given by the equation A equals the number of alleles after the bottleneck minus 1 divided by the original number of alleles minus 1. So here we have 1.9 3, 1, divided by minus 1, and then 2 minus 1 since we're still using that number. This will give us 0.931. So here, if allelic diversity is equal to 1, that means that the number of alleles is not changing. And if allelic diversity is equal to 0, that means that it is changing. So since this number is starting to get less than 1, that means that we are already losing allelic diversity after the bottleneck. From there, we already have allelic diversity and we have the original heterozygosity. So using the heterozygosity value from question A, what would the proportion of heterozygosity be if the population's bottleneck population lasted for 10 years? And from there, how much has it declined by the end? So here, we're pretty much going to use the exact same equation, except this time we are going to have all of this up to t, which is the number of generations. We are going to assume that generation is per year. So this will be the number that we had before for heterozygosity up by 10. This is equal to 0.4191. So the difference here, we have 9167 minus, so this means that we are losing this much heterozygosity over a 10-year period. Which is quite a bit of genetic variation. So is this population losing genetic diversity? Yes. It will be losing heterozygosity at almost a rate of 50% over just 10 years. So any catastrophic event, disease, or anything like that could easily wipe them out. So conservation plans would have to be pretty urgent at this point. Thanks for watching.